Assalamualaikum warahmatullahi wabarakatuh, and hi again. In this video, we will continue on simple linear regression and correlation part 2, which focuses on possible statistical inferences on the slope parameter beta in a simple linear regression model. Let's look at these part 2 learning objectives that you should be able to achieve at the end of this video. At the end of this video, you should be able to achieve the following part 2 learning objectives. First, you should be able to construct a confidence interval for the slope parameter, which is beta in a simple linear regression model. And second, you should be able to perform a statistical hypothesis test on the existence of linearity between a response or dependent variable usually denoted by y and a predictor or independent variable denoted by x. Let's look at how you can construct a confidence interval for the slope parameter beta in a simple linear regression model. Please note that in this chapter, we only make statistical inferences on the slope parameter beta and do not cover the inferences on the intercept parameter alpha. Back to constructing a confidence interval for beta, recall on the underlying assumption when we estimate beta by the least squares method. We assume that the errors are normally distributed with mean 0 and variance sigma squared, which is unknown and constant, where the error variance can be estimated as follows. The normality assumption of errors indicates that the response variable y, which is a linear function of the errors, will also follow a normal distribution but with mean response equal to alpha hat plus beta hat times x, which is the estimated regression equation. Under this assumption, when the sample size becomes large, by central limit theorem, the slope estimator beta hat will also be approximately normal with its mean equal to beta, and its variance is given by variance of beta hat. A random variable t defined by beta hat minus beta divided by the standard deviation of beta hat is said to follow a t distribution with n minus 2 degrees of freedom. We can actually borrow this definition of t statistic to construct a confidence interval for the unknown slope parameter beta. So for this beta, a 100 times 1 minus alpha % confidence interval for the unknown slope parameter beta is given as beta hat plus minus the margin of error, where the margin of error is defined as t-score at alpha over 2 and the degrees of freedom n minus 2 multiplied by the square root of beta hat variance, or simply the standard deviation of beta hat. The confidence interval can also be written like this, where the lower limit is beta hat minus the margin of error, whereas the upper limit is beta hat plus the margin of error. The variance of beta hat is by formula given by the ratio of estimated error variance to the sum of squares due to x, denoted by sxx. The t-statistic and the variance of beta hat formulae are available in the formula list of statistical table booklet, but the confidence interval formula is not directly given. Again, you can borrow the definition of t-statistic to construct the confidence interval for the unknown slope parameter beta. Please refer again at task 7.4 question 2 from Statistics for Engineers textbook in pages 153 and 154, which is on the relationship between the number of defective components produced by a machine and the speed of the machine. The sample data were given as follows. The question addressed in this slide is construct a 95% confidence interval for the slope parameter beta. Remember from part A of the test question that we have discussed in part 1 video on this chapter, we already obtained the sums of squares and the sum of product given as follows. Therefore, you can use these values to calculate the variance of beta hat first by substituting these values in the beta hat variance formula with a sample size n equal to 10. You may want to check that the variance of beta hat is given by 0.0007057. At this stage of calculation, you are advised not to round off the value of the variance of beta hat yet, because otherwise it may result in a large rounding off error in the final answer. Now if you look again at the question, you are to construct a 95% confidence interval for beta. In this case then, you should know that the level of significance alpha is 0.05. Please be reminded again, do not confuse between alpha used for the level of significance and the alpha used as an intercept in the regression equation. These are only common notations. Nonetheless, you must know which one is which and be careful when using these notations. Anyway, back to the question again, since alpha level of significance is 0.05, then you should use a t-score at 0.025, which is alpha over 2, and the degrees of freedom equal to 8, which is n minus 2, giving you the t-score value equal to 2.306 from the statistical table booklet, page 35. Hence, the 95% confidence interval for beta is beta hat plus minus the t-score times the standard deviation of beta hat. Replacing all notations with corresponding values, the 95% confidence interval for beta is then given by 0.2002 and 0.3226. Based on this confidence interval, you can be 95% confident that the slope is linearly positive, indicating a positive linear relationship exists between the number of defective items produced by the machine and the machine speed. Now let's look at the hypothesis test on the slope parameter beta. There are two approaches you can use. The first approach is a t-test approach, which can be used if you are interested to test if there is any linearity between y and x, or if you aim to test if there is a particular positive linearity between y and x, or if you want to test if there is a particular negative linearity between the two variables. Therefore, a t-test approach can cater for all these three hypothesis tests on beta. Alternatively, you can use an f-test approach. However, this f-test approach can only be used if you are interested to test if there is any linearity between the two random variables, where constructing an ANOVA table can be helpful in finding the f-test statistic for this approach. Back to using the t-test approach, the t-test statistic is given by the difference between beta hat and the value of beta under the null hypothesis H0, denoted by beta naught, divided by the standard deviation of beta hat, where you can find this formula in the statistical table booklet. Whereas the f-test statistic is simply given by the ratio of mean square due to regression denoted by MSR to the mean square error MSE. We'll look at these two approaches in detail in the subsequent slides. You may refer to the Statistics for Engineers textbook on page 156 for detailed explanation on the t-test approach when testing the slope parameter beta As mentioned earlier, you may have three options of statistical tests when using this t-test approach as listed in the following table. The first option is a two-sided alternative hypothesis where under the null hypothesis, beta is simply equal to beta naught, whereas under the alternative hypothesis H1, you will have a two-sided alternative hypothesis where beta is different from beta naught. The decision rule is to reject H naught if the modulus of t-test statistic is greater than a t critical value at alpha over 2 and degrees of freedom nu. As in chapter 4, when you have a modulus like this, you can use an alternative decision rule, which is to reject H naught if t-test is less than negative t alpha over 2 nu, or if t-test is greater than t alpha over 2 nu. The second option is a right-sided alternative hypothesis test, where under the alternative hypothesis H1, beta is greater than beta naught. Therefore, the decision rule is to reject H naught if the test statistic is greater than the right-sided critical value t at the whole alpha and degrees of freedom nu. Finally, a left-sided alternative hypothesis where under H1, beta is less than beta naught. The decision rule is then to reject H naught if the test statistic is less than the left critical value, which is negative T alpha nu. As mentioned in the previous slide, the t-test statistic is given as follows. Please note again that the degrees of freedom nu in this regression analysis is n-2. The value of beta naught is 0 in most cases, but at times you can also have beta naught value to be different from 0, such as in exercise 7 question 4c in page 174 from the Statistics for Engineers textbook. Another approach on testing the slope parameter beta is to use an F-test approach, which is explained in Statistics for Engineers textbook, page 159. When you use a t-test approach, remember you can perform only of three tests, either a two-sided, a right-sided, or a left-sided alternative hypothesis test. However, when you use an F-test approach, you can only have one option, that is to use a two-sided test only, where the value of beta under H0 is 0, whereas under H1, beta is not 0. That is, when you aim to test the existence of linearity, or if you test the significance of regression. Similar to a one-way ANOVA approach, the rejection rule is to reject H0 if the F-test statistic is greater than a right-sided critical value F at the whole alpha and degrees of freedom 1 and the sample size n-2. Please note that you do not have two critical values or two critical regions, although you have a two-sided test here. You only have one rejection rule, where the rejection region is only one, which is on the right of the F distribution. Now, how do you find the F-test statistic? A simpler way is to construct an ANOVA table like this, which is similar to what you have learned in chapter 6 on a one-way ANOVA. The first column is for the source of variations. While the total and error source of variations are exactly the same as in chapter 6, the treatment in chapter 6 is now changed to regression in chapter 7. The second column is for the sums of squares, where the total sum of squares SST is given by SYY. Next is the regression sum of squares given by SSR, which is equal to beta hat times SXY. The difference between SST and SSR is the error sum of squares SSE. The third column is for the degrees of freedom, The total degrees of freedom is simply n minus 1, whereas the regression degrees of freedom for a simple linear regression is only 1. Then the balance must be the error degrees of freedom, given by n minus 2. Getting the sums of squares in the second column divided by the corresponding degrees of freedom in the third column, now you have the values of mean squares in the fourth column, which are the mean squares due to regression MSR and the mean square due to error MSE. Please note that the MSE here is exactly the estimate of error variance sigma hat squared. Finally, the ratio of MSR to MSE is exactly the F-test statistic that you should use when performing the hypothesis test on beta by using an F-test approach. The previous slide was on general t-test approach in regression analysis. Let's focus a little bit on a specific test that is on testing the existence of linearity, or sometimes we call it as testing the significance of regression. For this particular test, as mentioned earlier, we have two possible approaches, either to use a t-test approach or to use an f-test approach. For the first approach, which is explained in page 157 under the null hypothesis H0, beta is equal to 0, whereas under H1, beta is different from 0. The rejection rule is then to reject H0 if the modulus of t-test is greater than t alpha over 2 and degrees of freedom n minus 2. You may refer to example 7.5 for this statistical test. Alternatively, you can also use an f-test or an analysis of variance or simply ANOVA approach explained in page 159. The null and alternative hypotheses are exactly the same as in the t-test approach, but the decision rule when using the f-test approach is to reject the null hypothesis H0 if the f-test statistic is greater than the right-sided f critical value at the whole alpha and degrees of freedom 1 and n minus 2, where the first degrees of freedom is the regression degrees of freedom, which is equal to 1, whereas the second degrees of freedom is the error degrees of freedom given by n minus 2. The concept used when using this f-test approach is exactly the same as what you have learned in chapter 6 on a one-way ANOVA. You may refer to example 7.6 for a practical example. To test the existence of a positive linearity, you only need to use a t-test approach where under H0 beta is at most 0 or simply equal to 0, whereas under H1 beta is greater than 0. Since we have a right-sided alternative test here, then the rejection rule is to reject H0 if the t-test statistic is greater than the right-sided critical value t at the whole alpha and degrees of freedom n minus 2. You may refer further to exercise 7 question 6 part C for a good practice. You may also want to test the existence of negative linearity. Again, you only have one option, that is to use a t-test approach in performing this statistical test. In this case, under H0, beta is at least 0 or simply equal to 0, whereas under H1, beta is less than 0, indicating a left-sided alternative hypothesis test. The rejection rule is then to reject H0 if t-test statistic is less than the left-sided critical value, which is negative t alpha with degrees of freedom n minus 2. Please note that you do not use the f-test approach in performing these two one-sided tests on beta. Please refer to sample data in task 7.4 question 2 again, where the data were given as follows. The question this time is, test if linearity between the number of defective components produced by the machine which is represented by the response variable y, and the machine speed, represented by the predictor variable x, is significant at the level of significance alpha equal to 0.01 by using A t-test approach as addressed in task 7.5 question 4, and B by using an f-test approach as addressed in task 7.5 question 7. Using either approach, the sums of squares and the sum of product as well as the estimated slope parameter beta hat obtained earlier are very useful in solving these questions. The hypothesis statements for both approaches are also the same, where under H0 beta is equal to 0, indicating no linearity significantly exists, while under H1 beta is not 0, which indicates that the linearity significantly exists between the two variables. Let's look first at part A on performing the hypothesis test by using a t-test approach in the following slide. For sample data from task 7.4 question 2 again, by using a t-test approach, under the null hypothesis H0, beta is equal to 0, which is indicating that there is no linearity between y and x, whereas under H1, beta is not equal to 0, indicating that the linearity exists between y and x. Since you should perform this statistical hypothesis test at the level of significance alpha equal to 0.01, the decision rule is then to reject H0 if the modulus of t-test is greater than t alpha over 2 with degrees of freedom n minus 2, which is equal to t 0.0058 given by 3.355 from the statistical table booklet page 35. As mentioned earlier, the t-test statistic is defined as follows. You can substitute beta hat with this value obtained from calculator directly and beta naught with 0. In addition, by using the calculated sums of squares and sum of product to work out the variance of beta hat as calculated before and substitute the variance of beta hat in the t-test formula. The t-test statistic is then calculated to be 9.84. Obviously, the modulus of t-test is clearly greater than the critical value, hence you should reject H0 and conclude that the linearity between the number of defective components produced by the machine, denoted by y, and the machine speed, denoted by x, significantly exists at the level of significance alpha equal to 0.01. Still using the sample data from task 7.4 question 2, if you want to perform an alternative statistical test on the existence of linearity using an f-test approach, then the hypothesis statements are exactly the same as those in the t-test approach discussed earlier, where under H0, beta is equal to 0, indicating no linearity exists between y and x, whereas under H1, beta is not equal to 0, indicating that the linearity exists between y and x. Again, you need to perform the statistical test at the level of significance alpha equal to 0.01. The rejection rule is then to reject H0 if the f-test statistic is greater than the right-sided f-critical value at the whole alpha on the right and degrees of freedom 1 and n minus 2, where n here is the sample size. So the critical value is equal to f 0.01 and degrees of freedom 1 and 8, given by 11.26 from the statistical table booklet page 40. Again, when using the f-test approach, the value of beta hat obtained directly from your calculator and the calculated sums of squares and sum of product are very useful in constructing an ANOVA table like this, as discussed in the earlier slide. Substituting the cell elements with their corresponding values, please check that you should obtain the following cell values in the ANOVA table, which results in the F-test statistic value equal to 96.92. In fact, if you do not round off any value from the beginning of the calculation, you should notice that this F-test value is exactly the same as the square of the t-test value obtained when using the t-test approach. Back to the F-test value, you can see clearly that it is far greater than the critical value. Therefore, you can reject H0 and conclude that the linearity between the number of defective components produced by a machine denoted by Y and the machine speed denoted by X significantly exists at the level of significance alpha equal to 0.01. In fact, this conclusion is exactly the same as what you had earlier when using a t-test approach. In summary, to test the existence of linearity or to test the significance of regression, you can either use a t-test approach or use an F-test approach. But please be careful when you write down the decision rules. Anyhow, using either approach should lead you to the same decision and conclusion. Let's look at another example, which is a post-final exam question based on a study on whether the average daily temperature has an influence on electrical consumption. Here, the temperature should be the independent or predictor variable X, which could have an influence on the electrical consumption, where this electrical consumption should be the response or dependent variable Y. The observed sample data were given as follows. Assuming that the two variables are normally distributed, the question asks if there is a significant positive relationship between X and Y at the level of significance alpha equal to 0.05. To answer this question, you only have one option, which is to use a t-test approach, since this is a right-sided alternative hypothesis test which involves testing if beta is positive or testing if beta is greater than 0. Therefore, you should not use an F-test approach for this question. Before you proceed to the test procedure, you can insert all the data in your calculator and extract all important statistical summaries that will be useful to answer this question. You can check if the statistical summaries are given as follows. Using these summaries, you can then calculate the sums of squares and the sum of product as given in this table. Now you should be ready to perform the correct statistical test to solve the problem as shown in the next slide. Continue with the example from the previous slide. After calculating the sums of squares and the sum of product, you can calculate the variance of beta hat that will be used to find the value of t-test statistic to solve this question. Since the question asks if a positive relationship exists between the average daily temperature X and the electrical consumption Y, then under H0, beta is at most 0 or just equal to 0, which indicates there is no positive relationship between X and Y, whereas under H1, beta is greater than 0, indicating that there is a positive relationship between X and Y. You need to run this test at 0.05 level of significance. Therefore, the rejection rule is to reject H0 if the t-test statistic value is greater than the right-sided t-critical value at the whole alpha 0.05 and degrees of freedom 9, where 9 is the sample size 11 minus 2. You can look at your statistical table booklet page 35 and check if the critical value t 0.059 is equal to 1.833. Now the t-test statistic by definition is given by beta hat minus the value of beta under H0 divided by the standard deviation of beta hat. replacing beta hat with 0.1024, beta naught with 0, and the variance of beta hat as calculated before, you can check that the theta's statistic value is given to be around 15.34. Based on this value, which is obviously larger than the critical value, you should then decide to reject H0 and conclude that there is a significant positive relationship between the average daily temperature X and the electrical consumption Y that evidently exists at the level of significance alpha equal to 0.05. We are now at the end of this video. Let's look at the achievement of learning objectives so far. By now, if you actively involve in learning activities, you should be able to achieve all Part 1 learning objectives covered in the first video of this chapter. And for this Part 2, you should be able to construct the confidence interval for the slope parameter beta, and you should also be able to perform a hypothesis test on beta correctly when investigating the existence of linearity between X and Y. To complete this chapter, you also need to learn how to find and interpret the correlation between the two variables X and Y, as well as learn how to perform the simple linear regression analysis by using Microsoft Excel. These last two learning objectives will be explained in the next and last video on simple linear regression and correlation. Until then guys, Assalamualaikum warahmatullahi wabarakatuh, and I'll see you again in the next last part very soon. Thank you for watching.